All right, enough drawing two-dimensional Lewis structures. It's time to start thinking about what these molecules would look like in 3 dimensions. And for that, we use the VSEPR theory, which is something that I'm hoping is familiar to you from first year chem. There it is, the valence shell electron pair repulsion theory, which helps us to predict a 3-dimensional shape of a molecule. Now, throughout this little chart here, they're going to ask us to draw all the Lewis structures. That's always the first step. You know, if this were a multi-step free response question, one of the early steps will always ask us to draw an acceptable Lewis structure. So this might be a fun little game to play. You may want to pause the video at this point and go through and try drawing all these Lewis structures yourself. And then as we look at the structures, see if you drew them right. I've got them all drawn in so that we can really focus in this video more on the VSEPR theory and assigning these 3-dimensional molecular geometries. So I'm not going to take the time to go through each of the Lewis structures. Some of them are like brutally easy, but there are some good ions and there are some kind of crazy ions toward the end of this chart. So you may want to pause it, go through and sketch these Lewis structures, check the overall electron count and see if that matches the amount of electrons that you drew in your structure. And then as we go through the rest of this video, you'll have the Lewis structure part done, which is kind of what I've done here. So if you're feeling up to it, pause the video at this point, draw the structures, and then I will be back with you very shortly. Or right now. If you're like, I don't want to draw the Lewis structures. I mean, you can just sketch them in as we go. But these would be very common structures that you would want to be able to know how to draw. Acceptable Lewis structures. Now, I'm hoping that some of these geometries or these 3-dimensional VSEPR shapes are familiar to you. The VSEPR theory stands for valence shell electron pair repulsion theory. It's a mouthful. It makes you sound like really intelligent. If you go home and you tell your parents, yeah, you know, no big deal today, we just learned the valence shell electron pair repulsion theory, it's pretty easy. They'll think that you're like curing cancer or like sending rockets into space or something. They'll be seriously impressed. But really this makes sense. The 3-dimensional shape of a molecule is based on the idea that we're only concerned with the electrons in the outer valence shell. The outer shell is the shell that's involved in bonding, and that's where we're going to find, you know, bonding pairs of electrons versus non-bonding pairs of electrons. Hence, the electron pair part of the VSEPR theory. So we're looking at electron pairs in the outermost shell, and the idea that any electron is negatively charged, and so like charges should repel. That's the repulsion part of the VSEPR theory. So we're looking at 2 different kinds of electron pairs. There could be bonding electron pairs, or there could be non-bonding electron pairs, which we usually just refer to as lone pairs. Lone electron pairs. So we've always said, you know, like when you draw your Lewis structures, those lone pairs, those extra dots, are essential. You must draw in all the extra little dots, because not only do they prove that everybody has an octet that needs an octet, but they also are very important when it comes to predicting the 3-dimensional geometry of the molecule. Okay, so the number of bonding electron pairs refers to obviously the number of bonding regions, and we're most concerned with those bonding regions around the center atom. Same with the number of non-bonding electron pairs, these lone pairs. We're really only concerned with non-bonding electron pairs on the central atom. Maybe add that little blurb in there. There's going to be lone pairs of electrons all over the place, but the ones that really affect the molecular geometry are those non-bonding electrons, those lone pairs, that fall on the central atom. Make a note of that. Okay, so linear. Linear structures are really common. They're probably familiar to you. This beryllium dihydride, or maybe you'll just call it beryllium hydride. beryllium takes a deficient octet. He only has 2 valence electrons, so he's only going to make 2 bonds. So it's okay that there's less than an octet on the beryllium. And for that matter, it's okay that hydrogen has less than an octet, because he's only filling the first energy level, which can only take 2 electrons anyway. So he's all good. We're looking at the central atom, any kind of electron regions. That could include electron regions such as these single bonds, or it could include an electron region that's involved, that entails a lone pair, which we don't have on this beryllium. So I've got 2 regions of negative electrons. They're both bonding regions. Since those 2 regions of electrons are negatively charged, they'll repel and go as far apart as possible. The furthest that I could put those 2 regions of electrons is 180 degrees. I should know this. A linear structure has bond angles that are 120 degrees. Now don't worry about this hybrid orbital thing. We're going to hit that in chapter 9. So you don't have to worry about any of that for now. But I should know that a linear structure has 180 degree angles. I really need to be able to picture this in my head. Now here's something that will come up. What if you have like carbon dioxide, which kind of looks like this? And you're like, oh no, double bonds! Around that carbon, the central atom, there are 2 regions of negative electrons. It doesn't matter if they're single bonds, double bonds, or triple bonds. We're just looking for electron regions. This is considered 1 group of electrons. This is considered 2 groups of electrons. They're going to repel, go as far away as possible, 180 degrees. Carbon dioxide is a linear molecule. Same thing with this guy. Here's another real common one. Hydrogen cyanide. What if you had something like this? You got a single bond and a triple bond. It's still linear. You've got 1, 2 regions of electrons on the center atom. They're bonding regions of electrons. It's okay that there's a single bond versus a triple bond. They're all electrons that are all negative, will repel and orient themselves as far apart as possible. So we're looking for 180 degree bond angles. All of those are linear structures. So it doesn't matter if the bonds are double bonds, single bonds, triple bonds. That does not affect the shape. Okay, so linear, piece of cake. Our next option, these guys kind of go together. The trigonal planar and this bent. These guys go together. Trigonal planar is a structure that you've probably looked at in first year chem. You've got 3 regions of bonding electron pairs on the center atom and no extra lone pairs of electrons. Check your carbonate ion. Did you draw the carbonate ion correctly? This is kind of a tricky one because normally you'd think of carbon having 4 bonds, and then you think, well, how do I hook on 3 oxygen? Check the electron count. If you add the 4 electrons from carbon, 6 valence electrons from each of the oxygens, you get 22 total electrons. But with a -2 overall charge on the ion, you get to use 24 electrons and give everybody an octet. So it actually works out pretty slick. One of the oxygens will end up being a double and the other 2 are single. Around the center carbon, you've got 3 regions of electrons. 1, 2, 3. Those dashes represent electrons that are all negative. They'll repel, go as far apart as possible. The furthest I can get those 3 electron groups is 120 degrees. And it doesn't matter that one of them is a double bond and the other 2 are single. It doesn't affect the shape. I do need to know that trigonal planar molecules have 120 degree bond angles. Trigonal obviously means 3, so it kind of looks like a triangle. There are 3 atoms around the center. Planar means flat. It's a flat triangle. And in class, we'll look at those model kits, And then you can kind of like put these in your hands and actually like look at and feel this trigonal planar structure. It's a flat triangle with 120 degree bond angles. Same thing would happen with, like here's another real common one. Something like boron. Boron, let's do like trihydride. Something like this. Boron carries a deficient octet. He only has 3 valence electrons. He just bonds all 3. Boron is real common as having these trigonal planar molecular structures. This bent molecule, I'm hoping that the term bent is also familiar to you. Bent. Here's why these two go together. There are 3 regions of electrons around the center atom. Trigonal planar, all 3 are bonding regions. In a bent structure, you've got 2 bonding groups of electrons, and it's tucked in here. 1 non-bonding group of electrons, meaning a lone pair. But you still have 3 total regions of negative electrons. 3 regions of electrons that want to go as far apart as possible. So this bent structure is kind of based on the trigonal planar. This is a tricky one here, this nitrite ion. Check your nitrite ion. You know, right away I knew it was kind of going to be a little funky because normally I don't think of nitrogen as taking like 2 bonds. Like, how do you hook on the 2 oxygen? So I tried something. I actually tried that double bond oxygen one at the bottom. The 2 double bonds. So I know oxygen likes to make double bonds. That's a pretty stable option for oxygen. And then I checked the electron count. Nitrogen brings 5 valence electrons. Each of the oxygen brings 6 for 17, but then it's got a -1 charge, so you get to add 1. So this guy at the bottom here, this was kind of my first thought. But it's got 2, 4, 6, 8, 10, 12, 14, 16 electrons. It doesn't have enough. So that's how I knew this wasn't right. It looked kind of cool, and I like it when it's symmetrical, but it's not the true structure. It's really a single and a double. And now here's another thing that we should mention. Okay, so the way I have this nitrite ion drawn makes it look kind of linear. That Lewis structure is 1,000,000% acceptable. However, the next part of the free response question is probably going to say, what's the shape and what are the bond angles? Don't say linear. It's okay if you draw your Lewis structure as I have it drawn, with the brackets, the -1 charge on the outside. You do not need to draw your Lewis structures to the true 3-dimensional geometry. That would get a little crazy in some cases. But when they ask you for the geometry and the bond angle, you better say bent. Because here's what's happening. I have 3 regions of electrons on that center nitrogen. 2 of them are bonding regions. And again, it's okay that it's a single and a double. They count as regions of negative electrons. The 3rd bonding region is that lone pair. It's 3 groups of negative electrons on the central nitrogen. Those 3 groups repel, and they want to go as far apart as possible. So in my mind, I'm thinking this. I'm thinking about that trigonal planar structure, but one position is not really an atom. So I kind of like this. Like, if I made this like a ghost on top, this 3rd spot, that's the lone pair. Oh. And maybe like this is the single bond and this is the double bond, something like that. That lone pair on nitrogen is so important. It changes the shape from being linear to bent. And it's not 180 degree. It's closer to 120. And in fact, this bond angle in here is a little bit less than 120. Slightly less. than 120 degrees. A lone pair seems to kind of take up more space than bonding regions of electrons. So you would expect it to be like perfectly 120. It's actually a little bit less. That lone pair kind of squishes those two oxygen a little bit closer. Lone pairs seem to take up just a little bit more space in a bonding region. On the AP test, if you said 120, they'd give you credit. Or more likely, like if this was maybe multiple choice, they'd probably have it listed as approximately 120. So if you said approximately 120, you'd be totally fine. Do you see the difference between that trigonal planar and the bent? 3 regions of electrons on both central atoms. But in the bent structure, one of those regions is not actually an atom. It's a lone pair of electrons. So what you're left with really is not going to look linear, even though I drew it kind of looking linear, which is totally fine. I don't have to draw it to the true 3-dimensional shape as long as I label it as bent with bond angles of 120 degrees approximate.